Hello and welcome to a tutorial on Kaufmann analysis. So in the last two tutorials, we discussed mass defect and how it can be used to identify compounds as well as accurate mass, and formula prediction using isotopic pattern and how isotopic pattern can be used in mass spectrometry to identify chemicals. My name is Jeremy Colmel, Innovative Omics and faculty at Yale University, and today I'm going to be talking about how we can combine all those pieces of evidence, mass defect, mass and isotopic pattern, in what's called Kaufmann analysis, not to identify a PFAS molecular formula or a PFAS structure, but to actually classify whether a molecule is PFAS or not PFAS. So for example, let's imagine we're in an industrial setting and they wanted to clean up their smokestacks, and they wanted to know how much of the stuff coming out of our smokestack is still PFAS and how much is not. And so we can classify all those molecules as PFAS or not PFAS, regardless of whether we can identify them. So as we showed last time, the isotopic pattern can be used to identify a compound. So this would be the FluorMatch visualizer, which is in the FluorMatch platform, where you can use this interface in this open source software to see all of the labels of the different isotopes, and you can determine the theoretical percent which is given to you for that atom, and then also see that overlaid with the MS1 spectra to see what it looked like. You can also see the cleaned MS1 spectra just with the isotopic pattern and how well that matches the theoretical formula given by our formula prediction algorithm described in the last video. You can also look for the different ranks and see how close the isotopic patterns are to each other. As you can tell here, the isotopic patterns are very close, regardless of the different formula predicted, although the first one was the correct one in this case, and as we mentioned, we can get quite accurate results with formula prediction. Still, even if we don't know whether the formula prediction is correct or not, we would like to know whether this is likely a PFAS or not. And so we'll discuss how to do that here. So as we mentioned, there's different atoms have different isotopic profiles, the probabilities of certain isotopes occurring in nature, and what masses show how many neutrons. So chlorine has a isotope with 2 more neutrons at 37. That's quite highly abundant, so that makes it very easy. Bromine's another atom as well, where you can easily identify it based on its isotopic pattern. Carbon, very low isotope ratio, but at least we have many carbons in most molecules, so that still makes it easier. If we have 20 carbons, we have 20% of the C13. Also, we mentioned sulfur as a good isotope to use. But what about fluorine? Fluorine, as we mentioned 2 videos ago, has no isotope. The only isotope is the main one, 18.9984. There's no N+1, no N+2, and that makes it very difficult to use isotopic pattern to determine a PFAS species, but not impossible. We can think about the unique relationships of mass and isotopic pattern to identify likely PFAS, because fluorine does contribute to the mass defect, as shown 2 videos ago. We showed that it has a negative mass defect versus hydrogen, which is a positive. So we already know that there should be a specific region for PFAS in the negative mass defect region. But other molecules can still overlap here, so we want to be even more confident based on our mass that it is likely a PFAS species. We know that fluorine usually replaces hydrogen in a species, and we'll show an example in the next slide. And so a highly fluorinated species has a high mass to the same amount of carbons. And that's what Kaufmann introduced in 2022, and he introduced Kaufmann analysis. Now here, we'll look at the example that we pulled up before in previous tutorials of the fatty acid octanoic acid versus PFOA on the bottom. So same molecule, except for PFOA replaces those hydrogens with a fluorine. Now the mass of PFOA is 143 versus, for the fluorinated version, 412. So this is what we're going to leverage to determine what's a PFAS and what's not likely not a PFAS. Same number of carbons, but one is over 3 times heavier than the other, or about 3 times heavier. And that's because fluorine just has a higher mass than hydrogen. So if it's replacing, it's a mass of about 19, where hydrogen's a mass of 1. So it's going to be a heavier molecule. So now, if we can estimate the number of carbons, then we know that the ratio of the mass to the carbons, the mass should be much heavier to the same number of carbons for PFAS. So now we just have to estimate the number of carbons, and we can do that. So we need the mass, which we get from our mass spectrometry data. So we already had that. Mass defect we'll also use because we know that PFAS should be a negative mass defect. We talked about that all that is the mass of the molecule, the actual accurate mass we measure, minus the mass rounded to an integer. So it's called the nominal mass. We do have a slightly more sophisticated algorithm we use in Fluoromatch. All this work on Kaufmann, especially formula prediction, has been done by David Schiesel. And this is the algorithm we use just to take into account when you get to 0.5, whether it goes up or down could be based on an error and could cause weird issues. But anyway, for our estimated carbons, so we discussed we do need carbons to get this ratio to determine whether something's likely a PFAS or not, because we know the mass should be very high for the same amount of carbons. We use the isotopic pattern. If you remember from the previous video, we talked about the M+1 isotope of carbon. If we have 1 carbon, it's about 1.1%. If we have 2 carbons, it's about 2.2%, so on and so forth. So we can use that M+1 to estimate our carbons. And so we get this equivalent carbon by dividing the M+1 relative abundance by 1.11. So if the relative abundance is 1.11%, as you'd expect for something with a single carbon, and you divide it by 1.11, you get 1. If it's 2.2%, you get 2. So this gives you the equivalent carbons. Now, as we showed with these 2 examples, the one will have a much higher mass or higher for the same amount of carbons. So this would be the plot. So on the x-axis is the mass to charge divided by the equivalent carbon. Since our masses should be much higher for PFAS, we expect PFAS to be on the right side of this graph, to have a high mass for the same number of carbons. Mass defect we expect to be negative, as we mentioned in an earlier video, and so we expect PFAS to be lower on this plot. What we did, and this is work that both Jeremy Comel and Michael Kumer helped program and come up with the idea, is we created isolines using, again, the EPA's PFAS database. We know that we can get a nice isotopic pattern from all those formula in the database, and then we can use that isotopic pattern, that M+1 peak, to get the equivalent carbons, and we can map all of those theoretical values onto this Kaufmann space of mass defect over equivalent carbons versus mass to charge over equivalent carbons. And what we find is that the PFAS fall within a very tight region. And we can say that in red, 95%, for example, of PFAS fall within this region. This is a 3D kernel density showing where most of the PFAS fall in this Kaufmann space. And this is the actual EPA data plotted, each data point plotted in Kaufmann space with the confident hits from the FluoroMatch software, so most likely PFAS. And you can see that almost all of them fall within Kaufmann space. Interestingly, the ones that fall outside of Kaufmann space but are still likely PFAS were identified, for example, as biotransformation products, where they have glucuronic acids or large portions of them which are not fluorinated. This goes back to the question of what is a PFAS and what is not a PFAS. These don't have many fluorine, they just have a few. They fall out of that region. Now, here's another plot, and this shows in gray is E's, so those are the likely not PFAS. And you can see that they fall, again, very far to the left, right? Because they have lower masses. They don't have that fluorine to add to that mass. They have hydrogen, 1 versus 19. And so your PFAS, which are in red, are all the way to the right over here, as we'd expect. So you can see that the PFAS form a nice region on the x-axis, and also separate out based on mass defect on the y-axis. Here's one more plot. And so the data that we're plotting and that we plotted before is for AFFF, or firefighting foam contaminated soil. Again, National Institute for Standards and Technology distributed this sample to many labs to see the state of the art for PFAS, how we were doing. Now, it's very cool to see what this algorithm does. So in red is the expected region for PFAS based on the EPA database. Remember, we created this expected region. And you can see on the left is some confirmed PFAS, or very likely PFAS, and you can see that almost all of them fall within that region, just a few falling out. And then on the right is our non-expected PFAS, things that don't have any MSMS match, no database match, they're not expected to be PFAS, and they fall out of that region. They're not identified in that region. So it's a selective net, that little red net, that's going to capture PFAS in this Kaufmann space. And so a very powerful tool. Now I'm going to use the visualizer. So this is part of the FluoroMatch software, but you can do Kaufmann analysis in other software as well. And here you can see the FluoroMatch visualizer does come with a Kaufmann plot. And you can see in blue here is the region, those little crosses. These are, as I select over them, EPA, this is the source. These are the EPA PFAS database entries. And then the other dots that are not crosses are actual values that we identified. We can zoom in if we'd like to see some of this better. And so if you see unfiltered, you can see that there's clearly molecules that do fall within this region, and then those that don't. So we can do two things. One is we can use our flag. So if you already annotate a data set, you can put your own flag. So let's put 1. So this means I've already manually annotated this data set and confirmed these species. As you can see, the nice homologous series, nice retention time trends, and also most of these species fall within the Kaufmann region. Now, let's take off this filter, and what we can do in the software is we can look at the Kaufmann cutoff, and we can set this Kaufmann cutoff, let's say to 0.95, right? Or 0.94, so below 0.95. So now it's only things that fall within the 94th percentile of the Kaufmann region. And as we scroll down here, we can see that the only dots that are showing now are those within the Kaufmann region. And so you can easily filter and figure out what are likely PFAS within the software platform using this region, and then start to confirm and look through each one of these individual species and see if it's real or not. Now, with that, I'd like to thank you for watching and look forward to seeing you again at our next training video. Feel free to leave questions in the comments section, Also, you can visit innovativemics.com to download the software, as well as to find our contact, our services, etc. So again, thank you, and